Previously, we looked at the theory behind detecting possible lines from a series of points by looking at the bin with the maximum number of votes. That is, the maximum number of intersections inside the bin. We discussed that the bin with the maximum number of votes is the line we draw through a series of points. Whatever theta and r value that this bin belongs to, that's the line we draw since it was voted as the line of best fit in describing our data. We'll start implementing this by detecting lines in the cropped gradient image by setting lines is equal to cv2.houghlines p. The first argument is the image where you want to detect lines, which would simply be our cropped image. The second and third arguments specify the resolution of the Hough accumulator array. The Hough accumulator array, previously I described as a grid for simplicity, but it's actually a two-dimensional array of rows and columns, which contain the bins that we're going to use to collect votes, with each bin representing a distinct value of rho and theta. The second and third arguments are really important as they specify the size of the bins. Rho is the distance resolution of the accumulator in pixels, and theta is the angle resolution of the accumulator in radians. The larger the bins, the less precision in which lines are going to be detected. For example, imagine every bin in our array was so large, this is way too coarse in the sense that too many intersections are going to occur inside of a single bin. We need our bins to be sufficiently small. The smaller the row and degree intervals we specify for each bin, the smaller the bins, and the more precision in which we can detect our lines. Yet you don't want to make your bins too small, since that can also result in inaccuracies and takes a longer time to run. So what we'll do is we'll specify a precision of 2 pixels accompanied by a 1 degree precision. This needs to be in radians. 180 degrees is equal to pi radians, so 1 degree will simply be pi over 80. That is numpy.pi divided by 180, 1 radian. To demonstrate the effect of this early on, here's a sneak peek of the end result when we finally detect our lines. In this picture, the bin resolution was a row of 20 pixels and 5 degrees, whereas here it's 2 pixels with a single degree precision. Clearly this one is much more precise in its output. So that's it for resolution. The fourth argument is very simple. It's the threshold. To find and display the lines from a series of dots, we need to find the bins with the highest number of votes, right? Once you find that bin, you take its theta and rho value and plot the line. However, how do we know which bins to choose? What's the optimal number of votes where we can say, okay, draw the line that corresponds to this bin? Well, that's where the threshold comes in. Threshold is the minimum number of intersections needed to detect a line. As previously mentioned, in a series of points, the points of intersection in Hough space represent the theta and rho values of lines that are common between a series of points. For every point of intersection, a vote is cast inside of the bin that it belongs to, which represents a line with some value for rho and theta. There's 5 intersections here, so 5 votes, and we assign a threshold of 3. The number of votes in this case exceeds the threshold, and it is therefore accepted as a line that describes our series of points. If we assign a threshold of some large number, let's say 12, in this case we don't have sufficient intersections in our bin to say that the line belonging to this bin describes our data, and is therefore rejected. In the case of our gradient image, we'll have a threshold of 100, which I found to be an optimal value, such that the minimum number of intersections in Hough space for a bin needs to be 100 for it to be accepted as a relevant line in describing our data. The fifth argument is just a placeholder array, which we need to pass in, so just declare an empty array. Not much to it. The sixth argument is the length of a line in pixels that we will accept into the output, which we'll declare as a keyword argument. Min line length is equal to 40. So basically any detected lines traced by less than 40 pixels are rejected. And lastly, there is the max line gap keyword argument, which we're going to set equal to 5. This should be capitalized. This indicates the maximum distance in pixels between segmented lines which we will allow to be connected into a single line instead of them being broken up. That's all, guys. We just set up an algorithm that can detect lines in our cropped gradient image. Now comes the fun part, which is to actually display these lines into our real image. What we'll do is we'll define a function, def display lines, which takes in an image onto which we'll display the lines as well as the lines themselves. And before giving this any logic, we're going to go right back here and set line image equal to the return value of our function, which we're going to specify momentarily, but we'll just set it equal to the return value for now. Display lines, pass in our lane image, as well as the detected lines. And back to our function, similar to what we have in region of interest, we'll declare an array of zeros, line image is equal to np.zeroslike, with the same shape as the lane image's corresponding array. So it will have the same dimensions as our image, although its pixels will be completely black as all of them will have 0 intensity. And now all of the lines that we detected in our gradient image, will display them onto this black image. This is a 3-dimensional array. To check if it even detected any lines, we have to check if the array is not empty. That is, if lines is not none. If it's not empty, we'll loop through it for line in lines. If you print each line that we iterate through, print line. Back to our terminal, run Python, lanes.py. If you print each line, notice each line is a 2-dimensional array with 1 row and 4 columns. What we're going to do is reshape every line into a 1-dimensional array, such that line is going to equal line.reshape, and we're going to reshape it into a 1-dimensional array with 4 elements. And you know what? Instead of setting line is equal to line.reshape4, we can simply unpack the array elements into 4 different variables: x1, y1, x2, y2. And now what we'll do is take each line that we're iterating through and draw it onto our blank image. Thanks to OpenCV, we can write cv2.line. This function draws a line segment connecting 2 points. We'll draw our lines on the line image, the black image we just created. The second and third arguments specify in which coordinates of the image space that we want to draw the lines. So the second argument will be the first point of the line segment, which is simply x1, y1. And the third argument is the second point of the line segment, x2, y2. All right, so we've specified the coordinates in which we want our lines to be drawn with respect to the image space. The next argument is what color we want the lines to be. So we'll specify a BGR color of 255, 0, and 0. This should result in a blue color, since the red and green channels will have 0 intensity. And finally, the line thickness, which is going to have a value of 10. Obviously, the higher the value, the thicker the lines, and that is all. All of the lines we detected in the gradient image, in our cropped image, we just drew them onto a black image, which has the same dimensions as our road image. Now let's just go ahead and return the line image. Return line image. And over here, we're going to show the line image instead of cropped image. And back to our terminal, we'll rerun our code, python lanes.py. And as expected, it shows the lines that we detected using Hough Transform, and it displayed them on a black image. The final step is to blend this image to our original color image. That way, the lines show up on the lanes instead of some black screen. So what we'll do is we'll go back to our code and we'll set combo image. I'm sure I could have come up with a better name than that, but combo image is equal to cv2.addWeighted. And so what we're going to do with addWeighted is take the sum of our color image with our line image, which should now make sense to you as to why the background of line image is completely black, since that would signify pixel intensities of 0, and by adding 0 with whatever pixel intensities are inside of this image, inside of lane image, the pixel intensities for that image would just stay the same, it wouldn't change, because 0 plus anything doesn't really make a difference. It's only when we blend the pixel intensities of our lines to the original that we'll see a difference, since they actually have a non-zero pixel intensity value. Anyway, first argument is going to be the lane image, and we're taking the weighted sum between the arrays of these two images. We'll give our lane image a weight of 0.8. Basically, that's going to multiply all elements in this array by 0.8, decreasing their pixel intensities, which makes it a bit darker. It will be more apparent why we're doing this momentarily. The third argument is the second input array of the same size, and we know it's the same size because we gave it the same shape as our lane image array, but it's all zeros instead. But anyway, let's put our line image array, and we'll give that a weight of 1, multiplying all elements in this array by 1. And now when we add these two arrays up, this one will have 20% more weight, which means that the lines will be more clearly defined when we blend the two images. This image is going to be a bit darker, thereby better defining the lines that we're blending it into. Finally, there's the gamma argument, where we can choose some value that will add to our sum. We'll just put a scalar value of 1. It won't really make a substantial difference. And that is all. We detected lines in the gradients, placed these lines on a black image, and then we blended that image with our original color image. So if we replace this with combo image, run the code, python lanes.py, indeed blended both of our images such that the lines are displayed right on top of our lanes. That is all for identifying lane lines. You learned how to identify lines inside of a gradient image with the Hough Transform technique, and then we took these lines, placed them on a random black image which has the exact same dimensions as our original road image. Thereby, by blending the two, we were able to ultimately place our detected lines back onto our original image. In the next video, we'll further optimize how these lines are displayed.